Welcome to another fabulous day of Calculus 3. We're going to wrap up double integrals today, so we've got a lot to do. So take a look at example 5. We're given a double integral right here, and they want us to do some things. So step 1 is sketch the region of integration. Now, folks, when I do a double integral, unless I don't have to switch the order or things are okay, I almost always, even without them asking me, sketch the region of integration. It's good to know what goes with your double integral. So that's just a little tip for you. So I need to sketch this region. Okay, so before I start sketching, I want you to look at the limits, and we're going to write down the 4 equations that are associated with each of the 4 limits for these integrals, and those are the equations we're going to graph. So the outermost integral has to do with the variable y. So we're going to need to graph y equals 1 and y equals 0. I'm just writing that down, I don't forget. Now the inner integral has to do with the variable x. So I need to write down, let's see, x equals y squared for the lower limit, and for the upper limit, I have x equals cube root of y. Okay. So those are 4 equations I am going to have to graph right now. Now, the y equals 1 and the y equals 0, pretty easy. Those are just straight horizontal lines, no problems there. But the other 2 functions they gave me are functions of y, not functions of x. So your graphing calculator isn't going to be helpful. Now, you can go to an online grapher like I have. The online grapher I have, or you can go to GeoGebra and graph those. But before we do, let me do it. Here's a 1. Let me graph y equals 1. Okay, straight line. Y equals 0 is just the line that sits on top of the x-axis. Fine. Okay, now x equals y squared. You may already know what that looks like from your pre-calculus days. That's a horizontal parabola. But before I go ahead and graph it, let's solve it for y so you could see what's going on. It's instructive. So let's try to write it as a function of x instead of a function of y. So I'm going to square root both sides. What do you have to remember when you square root both sides? Somebody help me out.
Plus or minus?
Yeah. So you're going to go like that. And then you get y is equal to plus or minus square root of x. So you're going to have to graph both. You're going to have to graph y equals square root of x and y equals negative square root of x. Let's do that now. And this you can use your graphing calculator for because they are functions of x. So y equals positive square root of x looks like this, right? And so that's y equals positive square root of x. And y equals negative square root of x looks like that. So it's below the x-axis. So you can see that we did get our horizontal parabola after all by graphing those 2 equations. Fine. Now, what about that other guy? Uh-oh. X is equal to cube root of y. Ugh. I don't think I have that one memorized. So I'm going to write down x equals cube root of y. And let's try to solve this for y, like we did with the other equation. So we'll try to write it as a function of x. So I'm going to cube both sides, and you don't have to do anything other than cubing both sides. And so I get x cubed on the left is equal to y. Now, y equals x cubed is something that you can use your graphing calculator for. Certainly, a cubing function is pretty sweet. And I'm going to just try to shade it in here like that. Now, I've got a big mess. I've got 4 graphs. What do I shade in? If you shade in the wrong thing, prepare to die. And this is real tricky for students because they see, they get confused. They think both the x-axis and y-axis are doing things. But you have to remember, if you consider all of these as fences, these are all fences to my vegetable garden. Oops, why does that happen every time I do that? So all 4 of these that I've done in green, this is my vegetable garden here. No, it doesn't want to do. All 4 are fences. So what do I shade in? Where is my vegetable garden? And I claim it's right in here. That's it. That's the region of integration. And you always want to shade it in on a quiz or exam because I'm going to ask you to. If you fail to shade it in, even if the graphs of the curves are fine, you get no credit. Because that's the hardest part, is shading in what's so. So this is our vegetable garden right there. Now, this double integral that they're wanting us to integrate, because there's only a 1 in the integrand, besides the dx dy, it's understood that this double integral represents area. Well, area of what? Area of the region of integration, that little sliver there, that area of my vegetable garden. Yeah. So let's actually evaluate it. Now, folks, when a double integral represents area, and pretty soon you're going to see today we're going to do volume, you need to get a positive answer. If you get a negative answer, something went wrong. And I mean, really, like you're going to get pretty much no points at that point in time, because areas and volumes are only allowed to be positive numbers. So that should be a red flag if you're doing homework or you're doing a quiz or a test. The exam that some of us did a mistake on the arc length, some people got a negative arc length. Oof, yikes. Your arc length, it's a length. You got to get a positive answer. Negative answers are not okay for lengths, areas, and volumes, okay? Now, sometimes a double integral will give a negative answer, but that's when the double integral isn't representing an area or a volume. It's representing something else. Well, what's something else? I can't tell you yet. That's what you have to stay for the rest of the semester for. There are other applications of these multiple integrals besides area and volume. You'll see. But if you are doing an area or volume or an arc length, gotta get a positive answer. Okay, so let's go do this. So first I'm going to do the innermost integral. I'm going to integrate 1 with respect to x. So let me, oh boy, I just have no more room left. Let me open out a free page here. Oh gosh, darn it. Okay, so we basically have an area. Let me just copy down my double integral, because otherwise I'm going to forget what I got. Okay, let's just evaluate it. So you imagine there's a 1 there. Even if you don't see the 1, if there's nothing else there, it's understood. So the antiderivative of 1 with respect to x is x. And you're going to evaluate x. Please put a bracket over here on the right-hand side, not the left. Otherwise, I will dock you for bad notation. And I want a bracket here, not a parenthesis. Okay? Like that. And then using the fundamental theorem of calculus, you plug in the upper limit first. Okay, q root of y minus, and then plug in the lower limit. Okay, fine. And now this is an easy peasy single integral that, any calculus 1 student can do. Before I do it, though, radicals are evil. And I like to write my radicals using rational exponents. That way, when I apply the power rule for integrals, I don't go and mess it up. So applying the power rule, we're going to have the antiderivative of y to the 1/3 is y to the 1/3 plus 1, divide out by 1/3 plus 1. And then the antiderivative of y squared is y cubed over 3. And before I evaluate this antiderivative between the limits, let's clean that up. 1/3 plus 1 is 4/3. And dividing by 4/3 is the same as multiplying by the reciprocal, 3/4. So now let's go ahead and evaluate at the limits. So plug in the upper limit, that's easy. And then evaluate at the lower limit. Now I know the lower limit is going to be zeros here, but I'm making a point. Sometimes your lower limit won't be zeroed out, even though the lower limit is equal to 0. You have to be very careful. Like cosine of 0 is not 0, and neither is e to the 0. So be careful. All right, and then finish it out. What the heck is 3/4 minus 1/3? I get 5/12. Okay, and there's your answer, and that's the area of that little shaded region we have here, 5/12 square units there. Fine. Now the hard part. Letter C. Where is letter C? Somewhere around here. This is where we're going to switch the order of integration and evaluate the new integral. Oh, here was my place to graph it. Nice. So we evaluated it, and now they want us to switch the order. Now, folks, this is the hard part, okay? This is the part where students have some challenges because it isn't something they had to do in a previous class. And I encourage you to practice a lot on these. Otherwise, you're going to have problems on the exams and the quizzes and the final, because it's going to be on all three, like repeatedly. I won't quit. In fact, on the last module, when we get to vector calculus, I will still have you do switching order. So learn it now, so things will be nice. Okay, so what of it? How do you switch the order? Well, it's still going to represent an area. And the order that we're talking about switching is the order of integration. Instead of dx dy, the new one, we want dy dx. That's the plan. Okay, if I recreate this sliver here, this point right here is 1, 1, where they intersect. This is the sliver right there. Okay, so this was y equals x cubed on the bottom, and then this curve was y equals square root of x there. Okay, so let's do the outermost integral first, because it's always the easier one. Well, how come? Because the outermost integral, in this case, it's with respect to x, those limits have to be pure numbers. You're not allowed to have any variables on an outermost integral. That's forbidden. That's one of the big rules and regulations for iterating your integral. So what of it? So what's x doing on this little region here? Well, the lowest pure number that x gets is right there at 0. So that'll be the lower limit. And then the highest that x gets is a 1 on that little sliver of a region there. Fine. We're done with the outermost integral and its limits. But what about the innermost integral? A lot of students make the mistake of, oh yeah, you just figure out the pure numbers what y is doing. No, you don't. The only time that all of the a double integral's limits are pure numbers is if the region of integration is a rectangle. And I hope you can agree with me that that region does not look like no rectangle, okay? So don't be putting pure numbers on both these limits. Now, it's possible one of them might be a pure number, but in this case, neither of them are. Well, how do I deal with it? This is where your little man is going to come into the conversation. What little man? Since this choice of order of integration is known as vertically simple, the dy dx, you will now need to put a vertical little man in your region. Now he's going to be pretty tiny here. Here's this little man standing up vertically. Wow, that's pretty tiny. I hope you can see him in there. Poor guy. Help, I'm stuck in a bubble. Okay, now use the little man to help get your upper and lower limits. The man's head will be touching the upper limit, but that's this curve here, which had the equation y equals square root of x. And that's what we'll put there. And that's legal because this limit, which has an x in it, doesn't match the variable of integration. If that were the case, then we would have to rewrite the equation. Now, the man's feet are standing on the lower limit for y. So the lowest that y will get is what the man's feet are touching. And that is the cubic function, x cubed. And we're done iterating the integral. Now let's go evaluate it and prove to ourselves that we get the same result as the original order of integration. Okay, here we go. Innermost integral first. You're going to integrate a 1 with respect to y. Well, that's just going to be y. And then you'll evaluate y between the limits for y. And we already established that, excuse me, those were x cubed to square root of x. And we still have that outermost integral, so I'll continue to write it. And of course, we run out of room here. Oh boy. And then plug in the upper limit first, minus the lower limit. Okay. And now this is just an easy peasy single integral from your Calculus 1 days. Once again, radicals are evil. So I'm going to rewrite the square root as x to the half. And that way I can use my power rule. So the antiderivative of x to the half is x to the 1/2 plus 1, which is x to the 3/2. Divide out by 3/2, but that's the same as multiplying by the reciprocal, which is 2/3, minus, and then the antiderivative of x cubed is x to the 4th over 4, and then evaluate this between 0 and 1. You know, And then when you plug in the zeros, you're going to get a bunch of zeros. So then what is 2/3? Oops, 2/3 minus a fourth. Use your calculator and you'll see it's 5/12. Ah, that's the same answer as we got before. And it needs to be. And that concludes that example. Okay, so let's take a look at an example that's not in your course reader. I'll just write it up right here as we go on the fly. I've picked it out just for you. And if you're watching this at home, folks, our home viewers, once I put the problem up there, pause the video and see if you can't do it on your own also, okay? And the reason why I want to do this extra example here is similar to the example we did before, to give you a reason why you need to know how to switch the order, okay? So I'm going to start the problem for you to give you a little motivation on why you want to learn how to switch order of integration so that you're duly motivated to go practice, okay? So let's take a look at this example. So double integral, and you're going to integrate sine of y squared dy dx, okay? And the inner integral has limits x and then pi, and the outer limit has limits 0 and pi. Now, I'm going to sort of start the problem for you, okay? And then we'll pause it. So let's try and evaluate this integral. They didn't even ask us to sketch the region of integration. Yeah, and we may not have to if we're lucky. Lucky meaning this integral is integrable without having to switch order or sketch the region or anything. So let's just try. How am I going to integrate sine of y squared dy? I claim that this is not integrable, not even using integration by parts or any trig special identities. You know, good luck with that. It's not going to work. You just can't. Now, if it were sine of y dy, well, then that would be easy because the integral of sine is simply, you know, minus cos. But this is sine of y squared, and we don't have the du portion of this integral handy. So we're like, okay? So it's just not going to fly. So when you run into a double integral, where when you're trying to integrate and it's not integrable, that means that you have to do work. It means switch the order of integration, and then you'll hopefully be able to integrate. Now, why would that be the case? Well, let me just show you why it will be integrable if we did switch the order of integration. We're still going to have a double integral. We're still going to have the integrand. You just copy it down. When you switch the order, the integrand doesn't flip or anything. And what flips is these guys. These guys have to switch. So my order of integration is what we're switching. I want to integrate the dx first, then I can do the dy. Okay, now you're going to have to figure out what these limits are. And the viewers at home, you're going to have to do that. That's going to be the hard part. And then, well, how are we going to do that? Do we just swap these two integrals? No, you do not do that. No, 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 please don't. What you're going to need to do is step one, you're going to sketch the region of integration. You know, write down the equations, 4 equations that you'll graph, and then have those as fences for your vegetable garden, shade in your vegetable garden. And then you're going to have to, you know, figure out the limits. But you want to figure out what the direction of your little man is. So figure out, you know, are you going to have him vertical or are you going to have him sideways? And it does matter. So if you look at the new version that we want dx dy. This is known as the horizontally simple choice. And so you're going to want your little man to be lying on his side in your region, whatever your vegetable garden looks like. And then the man's head, whatever it's touching, will be the upper limit for your x. And then his feet will be on the lower limit for x. Once you do that, you'll be fine. Let's just actually integrate right now. Let me just show you what I mean. What is the antiderivative of sine of y squared with respect to x? Knowing that when you integrate with respect to x, you hold y constant.
It should be just x sine y squared.
Good. Yeah, and sine y squared is going to be treated as a constant multiple. So it just goes along for the ride. And then you'll evaluate x at whatever those limits are that you're going to have to go figure out. So my point is, when we left it in the original order of integration, when it was dy dx, can't integrate sine of y squared with respect to y. No can do. But if we're trying to integrate sine of y squared with respect to x, since sine of y squared is a constant multiple, you can integrate. And that's the beauty of switching the order of integration. So, okay, so let's see what happened here. When you're doing this problem, you want to sketch the region of integration. Even though they didn't ask you to, you better sketch it, because that's going to help you, rewrite what the limits need to be once you switch the order of integration. So I'm going to look at my limits here, and that's with respect to x. So x equals pi and x equals 0. I'll have to graph those two guys in a moment. And then the innermost integral has these limits, so I'm going to have to graph y equals pi and y equals x. So let's go ahead and graph all four of those guys. How hard could this be, right? They're just a bunch of straight lines. Now, pi is a number that's a little bigger than 3, so I'm just going to kind of ramp this up. So it's like 3.14, so we just want to make sure. So x equals pi is going to be a vertical line that intersects the x-axis at pi, fine. Y equals pi is a horizontal line intersecting the y-axis at pi, fine. X equals 0 is a vertical line on top of the y-axis. And then y equals x, okay, that's a diagonal line. Woo, boy, that looks pretty terrible. Okay, that's a diagonal line right there. Now, it looks like a big hot mess. What are you going to shade in? Because if you blow this step, I don't even grade what the rest of what you do. Seriously, I don't. I can't, because it means you don't know what you're doing. So I'm hoping that you notice that all four of these fences are surrounding this triangular region up above. Not the one that there's nothing touching the x-axis. In fact, the x-axis isn't even one of the fences. It's not one of the boundaries for my vegetable garden. So if you shaded this in, congratulations, you got some partial credit points, because that is the correct region of integration. Now, for this double integral has something other than a 1 in its integrand, so it's not representing area. Okay, I'll just tell you that right now. Well, is it going to give me the area of that triangle? No, because it's got something other than a 1 in the integrand, and double integrals that represent area would only have a 1 in the integrand. Okay, so now what? Well, now we know that our ultimate goal here, I started it down here, we want the new order of integration to be dx dy. That has to be the case, okay? Because we're switching it from what was the original dy dx, and we need it to be dx dy. So let's iterate the outermost integral first, because that always gets to be pure numbers, okay? Pure numbers. So look at this region, it's triangle. What's the lowest that y gets? Well, if you kind of look at the eyeball the y-axis, you can tell. The lowest y gets is a 0. So that's the lower limit for y. And the highest it gets was y equal pi. And so we're done iterating the outermost integral. Now, the inner integral is with respect to x. And you have to be careful here, because I saw some people wrongly put 0 to pi. No. Why not? Because when all four limits of a double integral are pure numbers, that would mean that the region of integration is a square or a rectangle. And I hope you could agree with me that this region is not a square or a rectangle. So all four limits can't be pure numbers. That's a big mistake. And I see students make that mistake all the time, and they still, don't review and don't try to figure it out. They think I'm wrong or something. I don't know. Well, how do we do it? I'm going to walk you through it. It's not as easy as you think. You don't just, I don't eyeball it and go, humana. That's the answer. I don't. It takes me a while to figure it out too. So if you do something where, oh, I can do it in my head, good for you, because I can't. And I've been doing these for a long time. So because dx dy is the horizontal choice for this order of integration, you have to put a horizontal little man. This is sort of like a cross section instead of a rectangle for the cross section, which you would draw a sideways rectangle. I like to draw a little man because it helps me better. I used to teach it with the rectangle, but then I saw a cool video that used the little man instead, and I thought that was sweet. So let's do the little man's feet first. Notice the little man's feet, no matter where I slide the little man, and his placement is arbitrary. As long as I have him lying down, like what if I put him over here instead? As long as I have him lying on his side, where his feet are facing to the left and his head to the right, we're fine. So, I can move him up here. Wherever I move him, his feet are always on the y-axis, okay? So the lower limit for x is the y-axis, but you're not going to write y-axis down here. That doesn't make sense. The equation for the y-axis is x equals 0. So boom, there it is, x equals 0. So the lower limit is a pure number. Well, I thought you said you're not allowed to have pure numbers. You misunderstood. I said you can't have both of them be pure numbers. Please don't misunderstand me. I have students who twist my words around and go, well, you said this, and I didn't really quite say that. So now what about the upper limit? This is where students go, well, look, the biggest x get, look at the x-axis, it's pi. Once again, no. Look at what the man's head is touching. Notice no matter where I place my little man, his head is on this diagonal line, which isn't way over here at x equals pi. So you could put for the upper limit the diagonal line here on the symbol, but that's not going to work. Oh well, what was the equation for that diagonal line? Well, the equation they gave when we were writing it down, y equals x. But why is it illegal to put x here for the upper limit of this integral? Anybody want to gander? That's a no.
Because the dx, you can't have it the same as any variable in the thing.
Very good, Kelvin. This cannot match. These cannot match. You can't have a limit on an integral symbol match the variable of integration at that moment. Well, shoot, then what do I put? What am I going to do? Okay, well, the way we were looking at y equals x is we were thinking about it as a function of x. Solve this for y, or excuse me, solve this for x. Get it written as x equals. Well, it already is. X equals y. Aha. And that's what you're going to put for the upper limit here. And if you got this far, I would give you some more partial credit points, because switching the order of integration is the big battle to be won in this problem. Sketching the region is hard, and then actually iterating the integral, switching the order, that's hard. Those two talents, if you can master those two things in the next 3 weeks, you're going to be awesome. Now let's actually integrate. Okay, so they said, and I told you that, hey, the antiderivative of sine of y squared with respect to x is sine of y squared times the x. And now we can keep going where the limits on the x are 0 to y. And we still have this outermost integral, so I'm going to continue to write it because I don't want to forget I still got that to go. And then when I evaluate this using the fundamental theorem of calculus, I'll just have y minus 0, which is just y, but I still have the sine of y squared, so I'll copy that down, times y, times dy, and I have the limits there. Now, this is just a calculus 1 problem. This is now just a calculus 1 problem. So, if you're good at calc 1 with u sub, so we're going to use the sine rule. Let me just remind you what the sine rule says when you're using u sub. Sine of u du is equal to negative cosine u. Don't forget that, okay? So when you're doing u sub in my class, if you want your credit, all your points, you will have to write down who the u and the du are. And if you don't, you will lose points. Don't tell me you do this in your head and other professors let you do it in your head and that was okay. In my class, you're writing it all down. You want to maximize your points? I'm telling you how. Now what? Well, good news and bad news. I have a y and a dy in the integral, but I'm missing a 2. I need a 2 in there to keep going because that's part of the du. Now, some of you solve for dy, and I don't do that, especially with variables. I simply, when I teach Calc 1 and Calc 2, I put in my missing number, put it in, but you're not allowed to just put numbers anywhere you want. So you have to put the reciprocal, multiply it in the front of your integral. Now, when I rewrite this in terms of u's, and yes, you have to do this intermediate step on your paper for me also, must do. I need to see it. And then what? And then you have the minus cosine u, and then substitute in, I'm going to rewrite it with minus a half cos of y squared, and then I'm going to evaluate minus a half cos of y squared, going from 0 to pi. So then I go negative a half cos of pi squared, and I'm just going to leave that because that's some disgusting number, minus negative a half cosine of 0, and I think cosine of 0 is 1, and minus a minus is a plus, so you're going to have this plus a half, okay? And I think that's the answer, yeah? And that concludes that example. So what's the point? To recap, when you're doing a double integral and you run into something that's not integrable at all, sketch the region, use it to help you switch the order of integration, and hopefully it will be integrable at that point, and then integrate. Now, it sounds really easy for me to say that, but it took us a long time. So I hope you can appreciate that even doing one of these problems could take you a long time. All right, now let's continue on. I got lots more to do. Example 6. Example 6 is kind of hard, and I usually don't give something this hard on an exam. However, the concept that arises from example 6, if you understand it, then you're going to be better at iterating your double integrals when you have to do the setup. And that's going to be what I'm going to get to today. Yeah. Here we go. Sometimes you need to subdivide a region into subregions in order to calculate the area. And you had to do this in Calc 1, and maybe you forgot, and that's okay. So here, we're going to graph y equals 4x minus x squared. That is a downward facing parabola that looks something like that. And then y equals negative 3x plus 6. Well, if I had 6 way up here, it's going to be a line that intersects the y-axis at 6 because that's the y-intercept. Well, that is a terrible straight line. I'm sorry. And then they said above the x-axis. So the region that we want to find the area is this right here. I just shaded it in. Right here. All of that. Fine. So go get an integral representing the area. Now we're going to use double integrals in this class. Now, whether you use a double integral or a single integral, because you could do this problem with single integrals because it is a calculus 1 problem, because you found area between curves in calculus 1. But we're going to do double integrals. So we're going to need 2 different ones, 2 separate ones. Why? Because this region, the way it is, you're going to have to notice, let's see, I'm going to notice here, that's what the vertex is more like right there. I'm going to have to chop this region in half. So I'll call this side region 1. And the right-hand side of the dotted line, I'm going to call it region 2, R2. So the total area is going to be the area of region 1 plus the area of region 2. Why do you have to split it up? Why can't you do it all at once? Because of the nature of the limits, okay? So region 1 is going to have a double integral to go with it, and region 2 is going to have another double integral. And because we're doing area, the integrands will be 1s, and then I'm going to choose my personal favorite order of integration, which is probably going to be yours also, dy dx for both, and then I'll add them together when I get done. Now what? Why do I have to pick 2? Well, let's look at region 1 first. The integral here is with respect to x, so I need to figure out this intersection point. Where do these 2 graphs intersect? Now, it looks like it's going to be x equals 1. So, but don't always depend on your eyeballs. I want to see the analysis. So this intersection point is a pre-calc problem, and you remember you set the two equations equal to each other. When does y equal y? When does 4x minus x squared equal negative 3x plus 6? Now, folks, one of the things that I found when I teach Calc 3 is I find that some students can be okay in calculus and be even okay doing some of the U sub or whatever, but they forget a lot of their algebra skills, and that can hurt. Because on the exam the other day, solving systems of equations is an algebra thing, and when you're getting extrema for a function, whether you're using a Lagrange method or not the Lagrange method, you have to know how to solve systems of equations. And so that is still a little bit of a struggle. And so I may want to tell you something that may not be your favorite thing to hear, but on midterm 3, I'm going to put another Lagrange problem on there because some people didn't get to it. So it's going to go back on the exam for midterm 3, as well as all this double integrals and stuff. Okay, I claim this is a quadratic equation. How do you solve a quadratic equation? Well, they taught you in algebra, get everything on one side and 0 on the other. Well, which side? It doesn't really matter. I personally like to choose the side that I'm going to have a positive leading coefficient, but that's just personal taste. You could apply the quadratic formula, although I claim this factors nicely. And this actually factors to x minus 6 times x minus 1. And then you know the drill. The ZPP tells us that x minus 6 equals 0 or x minus 1 equals 0. So we have two solutions. Now, one of them we don't care about, even though it's good. Like when x is 6, these two graphs intersect way over down there, but that's not going to affect us because we're figuring out area above the x-axis. But we do care about the x equals 1, and that in fact is going to be the lower limit for that outermost integral for the first region. Now, what about what x is finishing out? Well, right where this x-intercept is for the y equals negative 3x plus 6, which is a 2, is going to be the upper limit for x. Now the hard part, what is y doing? Because we chose the vertical simple choice of integration, you're going to put a vertical man, here he is, in region 1. That's a funny looking man, but you get the idea. His head is touching the upper limit, but that's 4x minus x squared. His feet are on the lower limit, but his feet are on that diagonal line. Well, that's y equals negative 3x plus 6. So I've iterated this integral, and I'll let you figure out how to integrate it. I'll just put etc. Let's do it's not that hard. Let's do region 2. Well, how come you even have to have region 2? Well, let's iterate. So the outermost integral is going to go from 2 to 4. Those are the x-intercepts for both graphs, respectively. Now, what about y? You're going to have to put a different little man in this region. His head is still touching that downward parabola. So the upper limit for y for this second double integral is 4x minus x squared, because y equals 4x minus x squared. But his feet are standing on the x-axis, but the x-axis has the equation y equals 0. So y equals 0 is the lower limit. And then I'll just put etc. Okay. Now, when you add the final results together, the final answer, and it better be positive because this is representing area, people, I get, I think I get 15 halves square units. Okay. I wanted to show you that example because I wanted you to see that some regions you can't treat with a single integral just because of the nature of it. That could happen. And it makes you smarter when you're doing these. Okay. Done with that example. New concept, average value. New application for a double integral. You can use a double integral to figure out the average value for a function of two variables. Now, let's remind you that you did average value back in Calc 1. So let's do a quickie, a review equation. The average value for Calc 1. So what do I mean by average value? Here you are in Calc 1. Let's say you had y equals f of x. And they want you to figure out the average that f of x takes on in some interval. You know, does it go high, low, whatever. So hopefully you remember that F bar, this is just some notation. I don't know if you used F bar for average, statisticians use it. Or maybe your book said F subscript AVG for F average. Either way, it's going to be 1 divided by the length of the interval here. This interval, the length of it is B minus A. And you're going to multiply by the integral going from A to B of F of X dx. Now, I don't know if you remember this formula from Calc 1, but I'm asking you to remember it. Because we're going to now extend it to a function of 2 variables. So when you're finding the average value of an integrable function over a region R, instead of an interval, we're doing it over a region because we don't have the concept of interval here in Calc 3. We integrate F over the region. And then this time, instead of dividing by a length, you see here, we divide by the length of the interval. We're going to divide by the size of the region, which is going to be the area. So our definition of average value, let me get rid of this, is going to be F bar, or if you prefer FAVG, is 1 divided by the area of your region times the double integral of the function. Now I'm going to put some weird stuff in here, so please don't freak out. Instead of dy dx or dx dy over here, I'm going to put something more generic, which stands for either dy dx or dx dy. You'll see dA. So just a side note here, dA means one of 2 things. It means dy dx or dx dy. Well, which one does it mean? Either or. It depends on how you want to set it up. It's very generic. Now, instead of putting limits on the integral symbols here, I'm not. I'm going to do something very generic. I'm going to put a big fat R down below. And that means, generically speaking, you're integrating this double integral over the region R. Okay, this is very common notation. You're going to see it the rest of the semester in my lecture notes. You're going to see it on quizzes, on homeworks, and on the exams. So I'm not just making this up. This is the way they denote a generic double integral. Okay, now let's actually do one average value problem, and then we're going to move on to improper iterated integrals, and then we're going to finally get to double integrals and volume. Yeah, big day today. I'm going to do it all. Okay, we're going to do an easy average value problem. We're just going to find the average value of this function. My erase tool is not working, sorry. Come on, erase tool. There you go. 4 minus x minus y. That's the function we'd like to figure out the average value. And folks, if I graph this, this is a plane. How do you know? Well, you replace fxy with z. That's legal. And then you get that. And you can rearrange this by adding x and y to both sides. And I hope it's more recognizable now. It's just a plane. Yeah. And you want to know what the average altitude is, essentially, the average z coordinate, the average fxy, over this region. Now, this is a rectangular region. How do I know? Because all of the limits on x and y are pure numbers. In fact, I could sketch the region right now. Check it out. Well, they didn't ask you to. I know. But I always like to. So they're telling me that x goes from 0 to 2, okay, and y goes from 0 to 3. And it's understood, since all 4 limits are pure numbers, this is the region R of integration. Nice. What does that mean? Well, it means it's going to be really easy to do this average value formula right here. Okay, let's do part of this formula right now because it's super easy. I think we can find the area of this region R because it's just a rectangle. So what is the area of the region R? We don't even have to use calculus for this. We'll just use, 5th grade math. Length times width. 2 times 3, which is 6. Yeah. Okay, so then your F average is going to be 1 over the area, which we just got, 6, times a double integral. And you'll put the function in the integrand. And I'm going to choose my personal favorite order of integration, because, that's how I roll, just because. But with a rectangular region, it really doesn't matter, because you got all pure numbers as the limits. But I like dy dx. I'm just comfortable with it. Personal taste. And then what is x doing? Well, x is going from 0 to 2. And then y is going from 0 to 3. Boom, I'm done. So let's just do this integral real quick. If I integrate 4 minus x minus y with respect to y, be careful. I'm going to keep the 1/6 here. I'm going to get 4y minus x y minus y squared over 2. And I have to evaluate that between the limits 0 and 3. Always substitute your upper limit first. Well, where do I substitute it in? Because I just integrated with respect to y, that means I substitute that limit into the y only. Like, don't blow this and then try to put it into all the other variables and you'll end up with a hot mess. Okay. So I'm going to go 4 times 3 minus x times 3 minus 3 squared over 2. And then minus, and then I'm going to put 0 everywhere there's a y, but I'll just end up with a bunch of zeros, and that's just a big old 0. So yeah, whatever. Okay, and now I just have a an expression. Let's clean this up a little bit. What do I have? 12 minus 3x minus 9 halves. Yuck. What is 12 minus 9 halves? I think it's 15 halves. So I'm just going to combine like terms. So I really only have to worry about integrating 15 halves minus 3x. Ah, that's easy. Come on, that's Calc 1 problem. And so my antiderivative looks like 15 halves x minus 3 halves x squared. And we're still multiplying by the 1/6. And then when we substitute these limits, you know, 15 halves times 2 minus 3 halves times 2 squared, and the 0 will just give us a bunch of zeros. And then I get 1/6 times the 2's cancel. Nice. 15 minus 6. And I get 9/6, but that reduces to 3 halves. Fine. Okay, and that's the average value for the function on that region. Now, average value doesn't have to be positive. It could be positive, negative, or 0. But if you're finding an area or a volume, those values and results have to be positive. So don't get confused and say, oh, the teacher said I had to have this, and then you're putting words in my mouth, okay? All right, let's do improper integrals. Now, folks, I'm a big fan of improper integrals. Like, you better know it, because I like to put it on every quiz, every exam, and yeah, it's going to be on the final. Why? Because you run into improper integrals a lot when you get to higher levels of math, including differential equations. Like, when you find, if you're studying that, you'll do something known as Laplace transform, and that involves some improper integrals. Yeah, it's fun. So what's an improper integral? Well, there's a couple types, but the one that we're going to look at are the ones that have infinity or maybe even negative infinity on one of the limits. That's how you know it's improper. So this example 8 I have here, I know that the whole shebang is improper because I have a limit that's infinity. Okay. Do I have to sketch the regions when I have limits at infinity? Well, I won't make you, but we can talk about it, because you should know. I love this stuff. It's so much fun. Okay, so let's just integrate this because I want you to see improper. This is not a hard problem. Okay, this is not a hard problem. It's easy. So first up, I'm going to do the innermost integral. I'm going to integrate with respect to y. What does that mean? Hold x constant. What does that mean? Well, this x squared just looks like a constant. You know, I'm just going to sort of pull them to the side. Let's look at 1 over 1 plus y squared and try to figure out if we can integrate that. Does anybody remember how to integrate 1 over 1 plus y squared?
Arctan.
Very good. Arctan of y. Okay. And you still have an x squared out here, and we still have the outermost integral, but we're going to evaluate arctan between the limits of 0 to infinity. So one of the reasons why I love improper integrals so much is it's a disguised way to make students not only integrate, but know their limit facts. So it's kind of a double whammy. I love these. That's why they're so important. because it's really a slick way of trying to see if you still remember your limits. So if you thought we were like not going to do any more limits for the rest of the semester, oops, here they are. So does anybody remember what arctan of infinity is?
Pi halves.
Very good. And how about arctan of 0?
0.
Good. And you still have an x squared here, and you're still going to integrate the outermost integral with respect to x. And then this is just pi halves, so I'm just going to pull it out in front. It's just a multiple, and now we have an easy peasy calculus 1 problem. Hey, how do you integrate x squared? This is not a trick question. Okay, x cubed over 3. And evaluated the limits, and we're going to get, ooh, what are we going to get? I think that reduces to 9. Final answer, 9 pi halves. So this means that the improper integral converges. Yay! Because sometimes improper integrals blow up. And we're done with that example. Yep. Improper integral. Now let's do one with a different flavor. That's improper. How do you know? Well, you got a couple infinities here. Now, folks, if I did have to sketch the region, what I want you to know is that I could sketch the region of integration. I mean, they didn't ask to, but it's important you should know this, especially when we hit polar. Like we want y equals 0 and y equals infinity. I'm just pulling these limits off and rewriting them as equations. How the heck would we graph that? I mean, come on, x equals infinity. Are you kidding me? Ha 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 ha. Well, let's do the easy ones first. How about x equals 0 and y equals 0? Well, x equals 0 is vertical. We got that. Now, there is no such thing as x equals infinity, but basically x starts here from 0 and goes out to infinity, and y starts here from 0 and goes out to infinity. So if I shade in the region of integration, if you can imagine, it's the entire first quadrant, you know, and it extends forever infinity. The entire first quadrant is the region of integration for this particular double integral. Woo! That's fun. And if you didn't have fun figuring out that region of integration, well, then I don't know what to say. You're not doing this class right. Okay, so I'm going to pull up a new page so we can talk about this because I'm already running out of room. Okay, so before I do this example, I want to show you how I'm going to make it easier for myself. Now, you can't do this little trick any old time, but it is instructive. So let's talk about a handy fact. Okay. I'm giving you this fact because I'm giving you all my gold for double integrals. So I think the book may or may not mention this. If it does, it mentions it very quickly, but I want to make a big deal about it. If you have your integrand that can be written as two separate functions, one that only has x's in it and one that only has y's in it, you can actually separate them into two factors. You can't always do this, okay? For this problem, you can. If you can do that, what you're allowed to do then is you're allowed to rewrite it as two separate integrals, single integrals, and then multiply the results. Okay, so this has to do with multiplication, not addition. So this has to be a multiply, not an add. Okay. Then you're allowed to do this. This is totally okay. You know, and you don't have to, but if you see that, you can do it. Okay, so is that the case for this mess? Yes. Well, what do you mean? Well, that exponential, after distributing the negative, let me distribute the negative first, okay? Then what? Did I copy that down right? Let's double check. Oh, no, it's, sorry, negative 2x plus y squared. Sorry, my bad. Copy it down one, negative 2x. Okay, now using exponential laws, I hope you would agree that I could rewrite that exponential as the product of exponentials. Yeah, this is true, right? So what? Well, if I rearrange this integrand where I put this x next to his buddy, the e to the negative 2x, and then I put the y next to his buddy, I will have successfully written the integrand as a product of a separate function of x and a separate function of y. So that's cool. So that allows me to do the following. This is legal. Okay, now the limits for both these integrals are that. Okay, let's do it. So now we have two improper integrals to go evaluate. One of them is a calculus 2 problem. So this one's calc 2. This one can be done by a calc 1 person. Well, how did you tell the difference? You'll see. And I want you to get this good at integration. If you're going to be spending your quiz or exam time thumbing through formulas or the course reader or a book, that means you're needing a little more practice integration. Okay? This is an IBP problem, integration by parts. I hope you can see it. So let's do this quickly. It's important. So I'm going to pick my u and my dv. My u is going to be just x. My dv is e to the negative 2x dx. Du is going to be 1 dx. And v is the integral of e to the negative 2x, not the derivative. Be careful. And that's going to be negative a half e to the negative 2x. So be careful. Then what? Well, when you do an integration by parts problem, you're basically saying your integral is equal to u times v minus the integral of v du. Do you remember that? I hope so. So you're going to go x times negative a half e to the negative 2x, and you'll evaluate that between 0 and infinity, minus the integral, going from 0 to infinity, of v, negative a half e to the negative 2x, du. But that's just dx. Okay? Now this is totally integrable. You can pull the minus a half out, so you'll have plus a half sitting in front of the integral of e to the negative 2x. And the integral of e to the negative 2x, we just said, was negative a half e to the negative 2x. Okay, so now when I write all these together, I'm going to have to evaluate negative a half x e to the negative 2x minus 1/4 e to the negative 2x, that whole mess between 0 and infinity. Now, when you plug infinity here, this is going to look like infinity e to the negative infinity. Bad news. That looks like infinity times 0, which is indeterminate. Okay, I don't know if you remember this from your Calc 2 days, but I like to bring in some Calc 2 material. Well, then what? And if your teacher was instructing you on these types, you were then supposed to rewrite your expression as a quotient and then try again. Oops, that's supposed to be positive 2x. And then when you substitute infinity here, or take the limit as x goes to infinity, you'll get infinity over e to the infinity, which is infinity over infinity. And now you can use okay, no, I don't want that, sorry. Then you can use L'Hopital's. But I'm going to use something quicker. Do you guys remember growth rates? When you're taking limits at infinity, you can invoke your growth rates. What do I mean? Who goes to infinity faster? A polynomial, which is in the numerator, or an exponential function, who's in the denominator? Anybody remember who goes to infinity fastest?
Exponential.
Yeah. So what does that mean this entire quotient has as a limit?
0.
Good. So this whole thing goes to 0. Okay, goodbye. You go to 0. Get out of my face. Okay, now what about this? Be careful. So you're going to go, all right, well, minus 1/4 e to the, and you have a negative infinity. But that goes to 0 also. The whole thing goes to 0. Not so fast, Kimosabi. What do you mean? Well, you forgot about the lower limit. What about when you plug in 0 into this big old antiderivative? Well, you'll have negative a half times 0 e to the 0. That's 0. Minus 1/4 e to the 0. Oh, but that's not 0. That's minus a 4th. Okay, save that for later. Now what? Go back here and try to do the other integral. Remember this? This is the Calc 1 integral. You do not need integration by parts. So no IBP, no integration by parts for this one. Why not? Because you're just going to use the exponential rule, which says the integral of e to the u, using u sub, du is e to the u. And then tell me the u and the du. And when you integrate by parts, I need you to tell me all four, u, dv, du, and v if you want your full credit. And yes, I'm into integration by parts in this class. Yeah. U is negative y squared. Du is negative 2y dy. And then what? Well, I have a y dy already in the integral. What am I missing? Oh, shoot, I wish there were a negative 2 in there. Oh, make my wishes come true. Put a negative 2 in there, provided you multiply the front of the integral by the reciprocal. That way you're really just multiplying by 1, special version of 1. So now this looks like negative a half e to the u du, but that's going to be negative a half e to the u. But then when I replace u with negative y squared and evaluate this between 0 and infinity, we're ready to rock. So you're going to have negative a half e to the negative infinity. If you want negative infinity squared, but that's still negative infinity. This goes to 0. Yeah. And then what? While I was looking at this, I just noticed that when you plugged in the 0, you have minus, and then you have your stuff that you plug in with 0. So this negative has to distribute. So you really have a minus of 1/4 here. So this really should be a plus 1/4 that we were saving down here. I apologize for that. See, it even happens to your instructor where you mess up and miss a negative. Okay. So when you're doing this one, we don't have 2 terms in our integral, so we don't have to distribute anything. So we do have a minus. We have minus a half e to the 0, but that's going to be plus a half. Okay, now you're ready to wrap this up. Final answer is 1/4 times 1/2, and you get 1/8. Woo! And that is the answer to this double integral. That was very improper, that we had to do a lot of work on. Okay? And I think it's very instructive to do improper integrals. Okay? I'm really into improper integrals. I'm an improper integral type of girl. And you'll see next week when we get more into more stuff, I may whip out that testimonial of that student who is having to do not just double integrals, 6 integrals in his thermodynamics class. And most of those are improper. Okay? And he did have me for Calc 3. Okay. So there's a meme for you. Okay. So I think what I'm going to do is I'm going to get through deriving the double integrals soon. And then I'll do a couple of double integral problems and then I'll call it. And then we'll wrap up that on Friday, and then we'll get into polar coordinates on Friday. Yeah. Good news, polar won't be on this coming quiz, but the next quiz will be. So I skipped a problem, but I want to back up to it. This is not an improper integral. Well, how do you know? Well, it doesn't have any limits that are infinity. Well, why are you doing it as a grand finale? Because I like it. It has a little something that's weird that you have with double integrals, but not single integrals. And I find if I don't cover this, when those problems appear on homework and quizzes and exams, students are like, I didn't know you could do that. Yeah, so I'm going to do it here in lecture. So then you'll know you can do this. Okay. So why am I throwing this weird problem in here, and why do you even think it's weird? It doesn't look weird right now. Well, it's going to turn out that when you're using u sub, and you identify your u and your du, the du portion, which typically involves a missing constant, which is very easy to supplement in there, this is going to be a variable, but because you're integrating with respect to the other variable, that looks like a constant. So you're allowed to put one in. It's really weird. So I thought it was exciting enough to put it in my lecture notes. So you'll see. You'll thank me later. Here we go. Good news. We don't have to switch any order of integration. Okay. So it's going to be okay to factor in a variable, which you're never allowed to do in a Calc 1 class, provided that it's considered a constant with respect to W period, R period, T period, the variable of integration. Okay? What are you saying? Just write it down, and then after I do the example, it will make more sense. So we're going to integrate this, and yes, we're going to use the exponential rule, which says the integral of e to the u du is e to the u. We're going to need that to do this problem. Okay. Zero room. Okay. So who is the u here? So if you look at here, we're going to integrate that exponential with respect to x. I claim it's doable. U is x over y squared. So what's du? Now be careful when you're getting the du here and you're doing your u substitution, because you're integrating with respect to x. When you get your du, you have to differentiate with respect to x. Well, the derivative of x over y squared with respect to x is 1 over y squared in a dx. But I don't have a 1 over y squared sitting around in that integral. Well, I'm going to need one. Otherwise, you can't continue. Well, are you just allowed to throw one in there? Yeah, you put one in like this, provided you multiply by the reciprocal on the front of the integral. And we still have the outermost integral. I'll just keep writing that down. So this is totally legal, because y is considered a constant right now. So multiplying by 1 over y squared, you're multiplying with a constant multiple, and then, here you're really multiplying by a special version of 1. So now this integral has that look of the integral of e to the u du. And now that's just going to be e to the u, which for us is e to the x over y squared. And we still have this other y squared that we had to bring into the conversation sitting out there. And then we're going to evaluate the exponential between the limits, which in this case were 0 and y squared. That was 1. And now, what the heck? Well, now you're going to use the fundamental theorem of calculus, and you're going to substitute the upper limit right where the x is, and then substitute the lower limit, like so. And, y squared over y squared, doesn't that reduce to a 1? And e to the 0 is just a 1. And so when I get a weird constant multiple, this is just some weird number. It's a multiple. I just pull it out of the integrand. In other words, stick it out in front because it's weird. And that's legal. It's just a multiple. And now all I have to do is worry about integrating y squared. And that's a calculus 1 problem. So we can all do that easily. We still have that weird multiple sitting out in front. Okay, fine. And then evaluate between the limits of 2 and 1. Fine. And then clean it up. And your final answer is weird. It's this e minus 1 times 7/3. I know, weird. Okay. But the point being that when you're using u sub, and you may need a constant that's considered a constant with respect to the variable of integration, that's cool. Okay. So I did a lot of examples. I want to get into double integrals. Okay. So this is another application for double integrals, volume. So I'm going to quickly do a hand waving over how they came up with being able to use a double integral to give a volume of a solid, because it's a really cool application. And I'm just going to do the quick hand waving derivation here. I can do that because I have all the pictures here. So consider a continuous function f. That is a function of 2 variables. And just for ease, make sure that it's always positive. What does that mean? It's always above the xy plane. So they gave it right here. This sort of capping surface that you see here would be your function that's always positive because it's always above the xy plane. Okay? So that's it. Okay, fine. Now what? Well, the base of the solid that you're going to try to figure out this volume of down here is the base. That's your R. That's your region R in the xy plane. The goal is try to find the volume of that weird solid that's bounded above by the capping surface and below by the base here, the region R. So what they do is they put a rectangular grid on top of the base. That's a partition. And you've probably seen partitioning when you were in Calc 1. Do you remember they partitioned stuff with rectangles and stuff like that? Do you remember all that? We're doing the same thing right now. But instead of partitioning your interval down here into subintervals like you did in a Calc 1 class, the analog to that is partitioning the base of the solid into a bunch of little itty bitty rectangles. Okay. And they call that an inner partition. And they name the partition delta. Okay. And the norm of the partition is defined as the length of the longest diagonal of one of those little itty bitty rectangles. Fine. Okay, now they want us to choose an arbitrary rectangle in the partition. It doesn't matter where, just pick a point somewhere in the rectangle and then form a prism like so. And it's a rectangular prism, so you know how to find volumes of prisms. It's just the area of the base, which is going to be delta A sub I. That's the area of the base of the little prism, times the height. And the height is just this altitude, f x sub I, y sub I. That's how high it is. So your total volume of your prism looks like f evaluated at that arbitrary point, x sub I, y sub I, times the area of the base. Fine. And then you're going to make a whole bunch of prisms like so. Use a sigma to add them all together, and you got n of them. So I going from 1 to n, that's called a Riemann sum. And you'll get tighter and tighter approximations, better and better, as the mesh of the grid is forming smaller and smaller rectangles. And so eventually you're going to take a limit, and then the volume is defined as the limit as the norm of the partition goes to 0 of sigma f x sub I, y sub I, delta A sub I, like so. And what does that limit end up going to? Well, the sigma ends up turning into 2 integral symbols. Well, how come 2? That seems ridiculous. Shouldn't it go into 1 like we did in Calc 1? No, it's going to go to 2, and you'll see in a moment. Okay, so this is the official definition of a double integral. It's defined by a limit of a Riemann sum. And this is one of those generic double integrals I told you about, where over here you have dA, which could represent dy dx or dx dy, your choice. And you have an R down at the bottom of your symbol. And that just means over your region. And the region R is the base of your solid. Okay. And of course, provided the limit exists, then your function's integrable. Okay. Now, ratcheting up that definition to basically describe a volume. So the volume is just going to be the double integral over the region, fxy dA. Now, you are limited when you're finding volumes to keeping your capping surface above the region. Otherwise, you'll end up getting negative answers. And so you'll remember when you took a Calc 1 class and they wanted to find true area, they defined it where your function was a function that was greater than or equal to 0. It was above the x-axis. Because I hope you remember, if your function fell below the x-axis, when you were finding areas, sometimes your areas might be positive, negative, or 0. That's because you dipped below the x-axis. Similarly here, if your f of xy dips below the xy plane, you're going to end up with negative answers. So we're going to avoid that for now. And then how do you iterate this double integral? Well, it depends. If x goes from a pure number to a pure number and y is variable, then Fubini is going to help us iterate your double integral and have your outermost integral always have pure numbers. And then your order of integration would be dy dx for that one. On the other hand, if your region is described where it's horizontally simple and y is the one going from a pure number to a pure number and x is variable, well, then you'll set it up like this, where your order of integration will be dx dy. Okay. Now let's do a couple of examples and then we'll call it a day. I know I'm going late. Bear with me. You need to go? Go. Okay, can you guys see example 11, or is it covered up like mine is? Can you see that?
It's a little covered, but we have it right. So.
So you're going to try to find the volume of a solid. And you're bounding above by this plane and by the 3 coordinate planes. Now, you can easily go on a GeoGebra and graph this. And you guys know how to graph planes. So what I'm going to do here is I'm going to actually graph the plane by hand. And so you can see what the solid is going to look like. So graphing a plane by hand, you learned that 2 months ago. Find the x-intercept by setting y and z equal to 0. Find the y-intercept by setting x and z equal to 0, and then the z-intercept, okay? And there is the portion of the plane. Now, what's the other sides of this solid? It's bounded by the 3 coordinate planes, and you need to know this. You need to know when they say the 3 coordinate planes, what the heck does that mean? Well, it's bounded below by the xy plane, so there's the base. And then this side right here is the yz, coordinate plane. And then this other face here is the XZ plane. So I hope you can see this kind of looks like a tetrahedron. It's a 4-sided solid. And let's go find the volume of it. And because this is a setup from scratch problem, many students get very unhappy when they're asked to do these kinds of problems on homeworks and quizzes, which is unfortunate because they go, well, just tell me. I'm the kind of person who I like you to just tell me what to do and then I'll go do it. Well, these problems involve you doing the setup. Like this is all they're going to give you. Good luck. And if you're the type where you need it handed to you on a silver platter, it ain't going to happen. Okay? Yeah. So what do you mean? And yeah, this is going to be like one of the problems on this week's quiz. Like I'm not making this up. So the volume is equal to what? Help. Okay. Going to be a double integral. So start off like that. Ha 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 ha. And then here in the integrand, you're going to put the capping surface, which hopefully they gave to you. And then over here, you choose dy dx, or if you're weird, you can choose dx dy. And then iterate the double integral and then actually evaluate it. So this takes multi-steps. And there's another step I didn't tell you about. Yeah. So watch closely. So first up, they already told me the capping surface, but the problem is they didn't solve it for z. So I'm going to solve it for z because I need my fxy, which is the same as z. So there it is. So I'm going to put my capping surface here in the integrand. Okay. And then my personal favorite order of integration is dy dx. And now the hard part. How do I iterate, put limits on, essentially, my double integral? You don't just guess. The thing you're going to need to do, even though they didn't say it, is sketch the base of the solid in the xy plane. And this will help you finish out the problem. I'm telling you this because I'm giving you my gold. So take it as gold. Some people don't believe my gold. Sketch the base of the solid. Well, how do we sketch the base of the solid? Like, well, look at it. Look, when this plane, which is, I drew part of it, cuts into the XY plane right there, that's the trace. That's when Z is equal to 0. Z equals 0 in the XY plane. Okay, XY plane means Z equals 0. So then what? Well, then you get another piece of paper. Page. So then what you need is you need to have your XY plane, and then your plane equation was what? It was, where is it? X plus 2y plus z equals 2. Set z equal to 0 in the plane equation, and I get x plus 2y equals 2. This is what the trace is in the XY plane. So if you can graph this line, and I like to rewrite the line as a function of x. So if you solve it for y, I get y equals a half 2 minus x. And that's basically what's going on in the XY plane right there. And I'm only looking at a portion of it. because the sides of that solid are bounded by the x, or all three coordinate planes, they're also going to be bounded by the axes. So this right here is the base of the solid. Great. Now what? Use that to help you iterate your double integral. What the heck do you mean? Use it to help you put your limits on there. Okay. Since I chose dy dx, dx is the easier of the two to do the limits. It's always going to be pure numbers for the outer integral. So it looks like x is going from 0 to 2 on that triangular base. But what is y doing? Please don't put 0 to 1. Please, I'm begging you. You want to talk about begging? I'm begging you not to do that. Well, look at the triangle. Y is going from 0 to 1. Remember, only all pure numbers that the base would be a rectangle, which it isn't. Put your little man in there. His feet are firmly planted on the x-axis, which has the equation y equals 0. That's y equals 0. His head is on the diagonal line, which you already solved it for y. Y equals a half, 2 minus x. And folks, that is the volume. Now you're going to have to do a lot of work to integrate this. It is going to be a pain in the buttocks, because once you integrate with respect to y, you're going to have this. You'll still have to integrate later with respect to x. When you put this god-awful expression in place of the y, it's going to be pretty gross. And on a lot of the quizzes, because I don't want you to get bogged down in some calculus 1 integration with FOIL and all that, you can whip out your calculator and just use your graphing calculator at that point. And I get 2/3. So 2/3 cubic units is the volume of that tetrahedron. Okay? I know. That concludes that example. I'm going to set up one more and then say go use your graphing calculator and do the rest of the integration. The setup's the hard part. Let's look at example 12. Consider a solid region in the first octant. This is key that you know this. What is the first octant? In the world of 3D, we talked about this in the first week of class, but you probably forgot. There are 8 octants as opposed to quadrants in 2 space. The first octant is this region that's kind of coming out of the paper. It's where x is greater than 0, y is greater than 0, and z is greater than 0. And that means that your solid is going to be contained in that region. So that's key, because not all solids are. I may give you a problem where the solid isn't just constrained by the first octant. So they're telling us it's bounded by the 3 coordinate planes. Oh, does that mean it's another one of those tetrahedrons? No, this one is not a tetrahedron, because the capping surface is actually going to be the underside of a paraboloid. What the heck? Now, because we're bounded by the 3 coordinate planes, that means we're going to be in the first octant, which means we're in the first quadrant when we graph the base of the solid. Well, how do we graph the base of the solid? This paraboloid, do not set z equal to 0, because it doesn't have a trace in the xy plane like that plane did. What do you mean? Well, if you graph this paraboloid, you'll notice, I'm going to get into GeoGebra, what the heck. It's an upward facing paraboloid, so it's kind of like, oh man, it's kind of pretty actually. That's your capping surface. That's the upper portion of your, well, I didn't even know it saved stuff, weird. So if I graph this puppy in GeoGebra, see if it does it. There it is. So do you see that that's the underside of our, that's going to be like the ceiling. We're going to have a really weird room, okay?
Okay, Professor froze. I thought it was me. Professor, are you there? Okay, now she left. Clayton, you're the host. So just, yeah, you're the host now. Yeah, teaches Clayton. Class is over. Lamal, dude. I also need to, I should have been in another class by now.